I was asked to talk about Casimir effects for a general audience. This will be sort of horribly old-fashioned physics for some of you. There will be no Alice or Bob, only Hendrik Casimir, and a few others. This is a photograph taken from the AIP. The point is, this is Casimir around 1950 when he did his pioneering work on the consequences of electromagnetic zero-point energy. And that's really what Casimir effects are all about. He did this work in the late 40s, which is about, can't read this very well, somewhere around here, I guess. But in 1994, when I wrote a book that had 2 chapters on the Casimir effect, I made a plot that went up to here showing that there was growing interest in the effect. This is to only one of the major paper that he wrote. He wrote a couple of papers, but this is to a particular paper, 1948. And my friend Steve Lamoureux, in a review of 2005, carried out my little graph up. And you can see that the interest in the subject has grown considerably. One of these days I'll update this, but I did look at 2010. It is up here, so it continues this parabolic sort of growth. Somebody in a talk I gave recently said that pretty soon we'll have to measure this on a log scale. And I reminded him of the joke by Rudy Parles, which is that if the hard copies of Physical Review on your shelf keep growing at the rate they're presently growing at, that eventually the velocity at which it moves on the shelf will exceed the speed of light in vacuum. But there's no violation of relativity because no information is being transmitted. Okay, now, well, I don't know if that's true here, but maybe there's some element of truth in that. Okay, first of all, what is, and by the way, please interrupt me. I really don't mind being interrupted. If you have any questions, I'll try to address them. Otherwise, we can talk after the talk. So first of all, what is the Casimir effect? Casimir effect, usually, there are a number of different types of Casimir effects, but usually when one says the Casimir effect, he or she means the remarkable attractive force between 2 parallel, perfectly conducting, uncharged plates at 0 temperature. This is something that you would never expect from Jackson's book, for example, or Stratton or Smythe. It's something beyond classical electromagnetic theory. Okay? Casimir in 1948 predicted this force based on a derivation employing the idea of changes in electromagnetic zero-point energy due to the mere presence of the plates. As you'll see, it's a small but measurable force, and it's caused a lot of consternation among some very good physicists. One of them was Julian Schwinger, who called this one of the least intuitive consequences of quantum electrodynamics. And Schwinger spent actually the last 5 or 6 years or so of his career writing various papers on the Casimir effect, trying to understand it without zero-point energy. Here's another example of someone who had a lot of trouble with zero-point energy. Pauli, at the end of his 1945 Nobel lecture, says that it's clear that this zero-point energy has no physical reality, whereas Casimir predicted a physical, measurable effect based on zero-point energy. Another example. Okay, first of all, here is the formula for the Casimir force between 2 perfectly conducting parallel plates separated by a distance d. This is the force per unit area. See, it goes as h bar. It's a quantum effect. 1 over the distance to the 4th for the force per unit area with separation of the plates. And this is what Casimir derived in the 1948 paper that I showed the citations to earlier. So here's one more example of someone who found this very surprising, I think as everyone does when he first sees it. What startled me, in addition to the crazy idea that a pair of electrically neutral conductors should attract one another, was the way in which Casimir said the force could be computed, namely by examining the effect on the zero-point energy of the electromagnetic vacuum caused by the mere presence of the plates. I had always been taught that the zero-point energy of a quantized field was unphysical. Indeed, when one writes Hamiltonians in quantum field theory, you often throw away the integral of 1/2 h bar omega, being just a constant additive term in the Hamiltonian. It doesn't affect commutation relations or anything like that. So the Casimir force, I think, as I've said, is small. If you plug in some numbers, you find that if you express the distance between the plates in microns, the force comes out to be minus, attractive, 0.013 dynes per square centimeter. So if you've got two plates separated by two 1 centimeter by 1 centimeter plates separated by a micron, the force is only 0.013 dynes. And I have very little intuition for what that means, so I can give some examples or other comparable numbers. This is comparable to the Coulomb force acting on the electron in the hydrogen atom, or to the gravitational attraction between two 1-pound weights separated by half an inch, or about 1/1000th of the weight of a housefly. I looked up the weight of a housefly on the web. So anyways, so it's a really, really small effect. Nevertheless, it's been measured, starting with the experiments of Lamoureux, who at the time was at the University of Washington in Seattle, later moved to Los Alamos, is now at Yale. Steve performed a Cavendish-type experiment. More recently, there have been quite a few number of groups working on Casimir effects. Moadine at the University of California, Riverside, Capasso's group at Harvard, Bresci and Onofrio, who's at Dartmouth, Decca at Indiana. And these experiments are ongoing. There's a lot of interest in Casimir effects. Experiments actually started in the 50s through the 70s, and sort of heroic efforts. If you look, for example, in a as an indication of why experiments had to be done beyond this, the experiments of Sparnay, reported around 1958, are often cited as confirmation of Casimir's prediction. Whereas Sparnay, I looked at Sparnay's paper actually, and it was the error bars are like 100%. So I figured it's not all that well established. And if you look in places, there is a very nice reviews of modern physics article by Stephen Weinberg on the cosmological constant problem. He talks about zero-point energy, and he says that the Casimir prediction was confirmed by Sparnay, and Sparnay was much more careful. He said that his results were not inconsistent with Casimir's prediction. So I think it's really these experiments, which are within the 5% or so accuracy, that we can really say that the Casimir effect is real and it's as Casimir predicted. Just to give you an idea of the sort of experiments that have been done, this is my colleague Moadine at UC Riverside. And here's the basic idea. I should point out that of those experiments, only one actually involved plates, because it's really hard to keep things parallel. These guys were able to get something like 10% accuracy using parallel plates. The other experiments have relied on the so-called proximity force approximation, where you have a sphere, and if the sphere is large enough, you can relate accurately the force between the sphere and the plate, typically a gold-plated surface here, to the force between two perfectly parallel plates. And so the idea is you have a cantilever here, you shine a laser, and then you look at the deflection of the laser beam after calibrating things. Obviously, very sophisticated experiments. This is 1998. This sort of started the modern era of Casimir experiments. Why are people so interested? Well, because of for basic physics reasons, of course, but also for possible applications in nanotechnology. You can imagine, for example, so-called quantum actuation, where you make use of the Casimir force to move gears in micro machines and things of that sort. However, I think that most of the interest is on the negative side, in that you worry about, if you make machines, whatever, small enough, and you have these attractive Casimir forces, it may be very deleterious to making various devices. So there's much current interest in the engineering of materials to produce repulsive Casimir forces. I'll talk about repulsion a little bit later. However, okay, I tend to digress. I'll try not to. Work so far, though, suggests that it's going to be really hard to realize repulsive Casimir forces for realistic materials, and that's just some work indicating that. Okay, so any questions yet so far? Okay, so how did the Casimir force come to be, and what's the physics behind it? Well, in spite of its implications for cosmology, the cosmological problem in nanotechnology, it actually has a very mundane sort of origin. Many years ago now, I wrote to Casimir. This is 1992, going on 20 years now. And I was intrigued by whether Casimir was at all influenced by the developments in QED at the time, the Lamb shift, vacuum polarization, and things of that sort, where people invoked ideas of zero-point energy. I'll talk a little bit about that later. And Casimir wrote back and he says, no, I was not at all influenced. I was not at all familiar with the work of Welton and others who did the work some of the work that I alluded to. I went my own somewhat clumsy way. I wish I were so clumsy. Okay, so let me sketch the history of my contributions. Basically what went on here is that there were experiments being done at the Phillips lab in the 40s on the stability of colloidal suspensions. Colloidal suspensions are stable if the forces between them are not strong enough to make them, stick together. So there are repulsive forces due to electrostatic stuff that goes on in these electrolytic solutions. There's also an attractive force due to the additive pairwise, by assumption, van der Waals forces between the colloidal suspensions. If those forces are strong enough, the suspensions would not be stable. When milk is homogenized, basically what you do is you break up the little fat particles into smaller pieces, so the net van der Waals forces are small enough that the milk doesn't cream. It stays like you want milk to look like. These were similar kinds of experiments, but what they found by comparing the Landau, Derjaguin, Overbeek, and I forget the other name, theory of colloidal stability, what they found was they couldn't get agreement with experiment unless the van der Waals forces between two molecules fell off faster than 1 over, the van der Waals interaction energy fell off faster than 1 over r to the 6th. And in particular, Overbeek suggested that maybe because of the finite speed of light, you would see a 1 over r to the 7th, or at least you'd see a weakening of the interaction at large separations. So they went to their theoretical colleagues at Phillips, Casimir and Polder, who tackled this problem in quantum electrodynamics. Basically what they did is just standard messy fourth-order perturbation theory, and they included retardation. That is, they included factors e to the ik dot r in the interaction, where r is the separation between the molecules. And what they found that was indeed that at large separations, meaning larger than about 137 Bohr radii typically, larger than a typical strong, the wavelength of a typical strong transition from the ground state, the interaction went, for distances larger than such wavelengths, the interaction went as 1 over r to the 7th instead of 1 over r to the 6th. And now, here's what's interesting. The point I should have mentioned in later publications, summer or autumn 1947, I'm not sure which, but he took a walk with Niels Bohr, and he told Bohr about his results for the 1 over r to the 7th, and Bohr said, that's nice, that's something new. I told him that I was puzzled by the extremely simple form of the expression, which I'll show soon, at very large distances, and he mumbled something about zero-point energy. That was all, but it put me on a new track. So I found by calculating changes of zero-point energy, as suggested by Bohr, that it really did lead to the same results as Polder and myself. Then, because of my position in the Phillips lab, I was somewhat familiar with the theory of modes of resonant cavities and their perturbations. So then he went on, based on the idea of zero-point energy, to predict, in this simple case of just the two plates, this force of attraction. So he said he didn't think that there were any outside influences. Now, I don't know whether Bohr, knew about this other work involving the Lamb shift and so on and had that in his mind, but as far as Casimir was concerned, he didn't have any outside influences. I did not myself contribute to further developments nor to experimental confirmations, apart from proposing a crazy model for the electron, which did not lead to a value of the fine structure constant. And if I have time, I'll talk about that. And Casimir said I'm free to publish this, so I show it with impunity. Okay. Okay, so van der Waals forces. Van der Waals, 1873, often described as a hapless 36-year-old graduate student when he did this work, and some years later won the Nobel Prize. The story's a little bit more complicated, but London, who so van der Waals, I think van der Waals actually, all I could find was a Yukawa type, what we would today call a Yukawa type interaction between molecules proposed by van der Waals. I think it was London who actually wrote down the 1/6 using perturbation theory. And what London found was the following expression. Okay, familiar 1/6 for van der Waals that we all learn about in high school. It goes as h bar, and then this is the integral of the dynamic, that is the frequency-dependent polarizability of two identical molecules, for simplicity here, evaluated at imaginary frequencies, and you integrate from 0 to infinity. That's just what you get by deforming your contour integral. You can write it in terms of imaginary frequencies, 1/6. What Casimir and Polder found in 1946 was that at large distances, this goes over to this formula, where now it's 1/7, and where now the static polarizabilities enter. That is, the polarizability is evaluated at 0 frequency. You might expect, because at really, really large distances, the frequencies sort of cancel each other out because of strong oscillations, so it's only the static part that matters. Sort of intuitive, I think. Casimir and Polder predicted another effect, on the way to this perfectly conducting plates business. They showed that if you consider an atom near a perfectly conducting wall, that there's actually an energy of interaction that goes as 1/d⁴, an attraction that goes as 1/d⁴, and again, h bar, static polarizability. You would expect, based on just the dipole interaction of an atom with its image, that the interaction ought to go as 1/r³, 1/d³. Whereas what happens at large separations, as in the two-particle van der Waals interaction, is that you get a weaker fall, or I should say a stronger fall-off with distance, 1/d⁴, not 1/d³. This was actually measured very beautifully by a group at Yale under Ed Hines at the time. And what these experiments did was, imagine you have a tube with perfectly conducting walls, and you send a beam of atoms through. If you assume this sort of interaction, then the atoms will be attracted to the walls. And if you assume that when an atom hits the wall, it sticks there without bouncing, then you can calculate, just based on classical Newtonian trajectories, what fraction of atoms should come through. Okay? And they did this experiment for sodium atoms, assuming this, and with no adjustable parameters, we're able to confirm this to within a few percent. Very beautiful experiment. So again, these Casimir effects have been predicted to really nice accuracy. Okay, so I want to bring in some other little things here. Namely, how did zero-point energy first arise in physics, in quantum mechanics? Well, I think the first time anybody ever wrote down an expression of that sort was Planck in his so-called second theory of black body radiation. In this theory, it's all very complicated from today's perspective, because notation has changed and so on. But basically, the idea in Planck's second theory in 1912, remember the first theory was 1900, was that an atom, a dipole oscillator, will absorb energy continuously until it reaches a certain level. Then it lets go of it right away, instantaneously, discontinuously, if you like. So an oscillator at frequency omega would absorb continuously until its energy becomes 1/2 h bar omega, and then becomes some integral of h bar omega, and then it emits. Along the way, Planck needed the average energy of an oscillator, a harmonic oscillator between n and n plus 1 h bar omega. That is obviously given by that expression. So you pick up this 1/2, and that's how zero-point energy first appeared in physics. And so he wound up with the expression for the average energy of harmonic oscillator frequency omega, temperature T, given by that expression. That's kind of interesting, because if you look at this, normally we would throw that term out, but if you insist that you should get the classical K, Boltzmann's constant, times T at high temperatures, to first order in h bar, you need to have this term. Right? You will get, if you expand this out, you'll get a kT minus 1/2 h bar omega, and you need this guy to give you kT to lowest order in the Planck constant. Planck didn't seem to take this very seriously in terms of the physical reality of it, but this gentleman did, at least in the beginning. And what he did in some very nice work with Stern in 1913 was to conclude that this zero-point energy is probably real. I forget the German word that they used, but it was probably real. How did they deduce that? Well, two things, remarkably enough. One, the Planck spectrum, and the other, the specific heat of molecular hydrogen. Right? Who would have thought it? So let me remind you of some things. In 1909, Einstein derived this formula for the variance in energy of a system in thermal equilibrium. Any undergraduate can do it. You write down e to the minus E over kT, sum over all the states, and so on. You calculate that. So now let's suppose that we're looking at black body radiation, and we want to consider the average energy in a frequency range from omega to omega plus d of omega contained in the zero-point field, in the black body field in a volume V. Well, so from the Planck spectrum, using this formula, you get that the variance in energy for radiation in this frequency interval around omega is given by this expression. It was just algebra from here in the Planck spectrum. And that is at least what used to be the famous Einstein fluctuation formula. And what's interesting about this was that Einstein pointed out that this indicates a wave-particle duality of radiation. Namely, this is a particle term, this is a wave term. Why is that a wave term? Well, if you just assume classical waves of random phases and calculate the variance in the energy, you get only this term. On the other hand, if you assume particles with Poisson statistics, you get exactly that term. So Planck's formula and Einstein's fluctuation formula gives both terms, indicating that light radiation has this wave-particle duality, the first indication of wave-particle duality. So what does this have to do with zero-point energy? Well, if we go back to Planck, one uses in classical theory the following expression for the energy of thermal radiation at frequency omega. It's the number of modes, omega squared over pi squared c cubed per frequency interval per unit volume. And then each of these modes classically has an energy kT, right? So what do you get? You get the Rayleigh-Jean spectrum. It's an inexorable consequence of classical physics. If you assume this rho in the Einstein fluctuation formula, you in fact, in this formula here, if you assume that expression for rho, if you use this formula and use for rho not the Planck spectrum but the Rayleigh-Jeans, you don't get this term. You only get that term. Another indication that that first term is associated with classical waves. Now, here's what Einstein and Stern said. This is all classical, but suppose we assume the reality of zero-point radiation, zero-point energy. Suppose we replace this formula where this U K equals kT is the energy of a harmonic oscillator in thermal equilibrium. Suppose we, instead of that kT, suppose we use this expression, which reduces to that in the limit of high T. Okay? Now what you get is the original rho of omega, of Planck, but now you've got another term associated with zero-point energy of radiation, of harmonic oscillators. This is a remarkable spectrum because it turns out to be the only spectrum that's Lorentz invariant. So if I look at the energy in a frequency interval from omega to omega plus t of omega in a certain volume, and I transform the volume and the frequencies by Doppler shifting, this is the only form of spectrum that gives exactly such that the numerical value of the energy in that interval doesn't change at all. Okay, so that's pretty. Einstein didn't seem to note that explicitly, but in another context, it was required that he should. Okay, so what happens now? So I include that. I include this term here, right? And now I go back to this expression. But I'm going to do everything classically now. I'm only going to keep this term. But for rho, I'm going to use this original rho plus the contribution from 0-point radiation, 0-point energy. So what do you get? You get in rho squared, you get a cross term that goes as what? Rho times h bar omega cubed divided by pi squared c cubed. You get a 2 because you square, right? So you get, when you include 0-point energy, you get, amazingly enough, the particle contribution to the Planck formula, to the Einstein fluctuation formula, which suggests that 0-point energy has something to do with particles, right? Something to do with this h-bar dependence, this apparently strictly quantum portion of the wave-particle duality formula. I'd like to point out a couple of other little things. Namely, if I write the Einstein fluctuation formula in terms of photon numbers, n, this will give me an n squared, that'll give me an n, right? So what does that tell us? That tells us that we have exactly the formula for Bose-Einstein statistics, which tells us that the 0-point energy seems to have something to do with the particle term, this additional term in the Bose-Einstein fluctuation formula. Or, since the variance, by definition, is given by that in photon number, I can write the average value of n squared is 2 times the average value of n quantity squared plus n. The 2 here is interesting. It is, in fact, exactly the 2 that implies photon bunching in the Hanbury-Brown twist effect. Now, I find remarkable that in recent years there have been pieces in physics today where they talk about the Hanbury-Brown twist effect and how important it is, and it's used in atom optics and so on, in particle physics. No one ever seems to mention that it's really due to Einstein, right? Fluctuation formula, wave-particle duality, all that stuff. It's simply a consequence of having this term, the wave term in the Einstein fluctuation formula, and the definition of the variance that you pick up the 2. This caused the Hanbury-Brown twist effect, when it was first discussed by Hanbury, Brown, and Twiss in the 50s, caused a lot of consternation. In fact, my late colleague Ed Janes told me once that some people thought that a hoax was being perpetrated. The reason is that people were wedded to this idea of Dirac, who said in his famous book, 2 photons never interfere with each other. A photon interferes only with itself. Something like that. That was in the context of the Young two-slit experiments, and he made that statement so that you wouldn't be violating energy conservation. What's really interfering here are, of course, probability amplitudes, not photons. So you can do an experiment in the laboratory, as Brown and Twiss, later Mandel and many others did, where you can see the factor of 2. You send incident thermal light filtered to limit the frequencies through a beam splitter. You have 2 detectors. And you have correlation electronics here, which tells you, which gives you the correlation, tells you what is it, the tendency of the photons to arrive in pairs. Okay, so I plot the average value of I of the intensity here at times t times the intensity here at time t plus tau, and I do this correlation, and I measure this quantity as a function of tau, and you see that I didn't put 2 here, but there's a 2 here. There's a tendency for the photons to arrive in pairs. At 0 time delay, there's more of a chance of coincidence that there is at large time. With large time delays, they come completely independently. And this, by the way, this width is determined by the bandwidth of the light. But there's this too. It's a real effect. The average value of I squared is 2 times the average value of I squared. So, but this, I want to point out that, or emphasize that this reflects nothing but the wave term in the Einstein fluctuation formula, that little 2. Okay? Now, as far as people having trouble with this, what Brown and Twiss were interested in was not so much this fundamental business, but in making a stellar interferometer, an intensity interferometer. And this is the basic idea. The same kind of correlation that's in that laboratory experiment with the filtered light and so forth. So you've got 2, let's say, stars here, and 2 detectors on Earth. This is just a schematic. These don't have to be equal distance or anything. So if you perform the same kind of analysis that I showed, essentially, what you find is that by varying the detector, the telescope separation here, you can get information about the angular separation of those 2 sources. And what's interfering, as I said earlier, are not photons but probability amplitudes. Namely, in this case, you have two possibilities for getting photons at both places. Light can come that way or this way. So you have two probability amplitudes that you add for indistinguishable processes. You square, you get Hanbury-Brown twist type correlations. Here's an example of someone who had trouble with this. At a Caltech colloquium at which Hanbury-Brown talked about it, Richard Feynman jumped up and said it can't work. In his inimitable style, Hanbury responded, "Yes, I know, we were told so, but we built it anyway, and it did work." Late that night, Feynman phoned and woke up Hanbury to say, "You are right." He also wrote a letter in which he magnanimously admitted his mistake and acknowledged the importance of this phenomenon that at first sight appears counterintuitive even to quantum theorists. So Brown and Twist went on to measure the angular separation of the Sun and 32 other stars, I believe. Nowadays, of course, it's all done with amplitude interferometry, Michelson type rather than intensity. But it's interesting to me that it goes back to Einstein in this connection, mysterious connection with zero-point energy. So I'll remind you of some very simple quantum mechanics of the harmonic oscillator, namely that zero-point energy here arises from a non-vanishing commutator between A and A dagger. I can write this like that. I pick up a 1/2. And I can write down what the variance is in general. You have this term, which we can associate with the wave term. For example, if I'm in a perfect coherent state, an eigenstate of A, this term would give 0, no wave-type fluctuations, and I'm left with only the average number of photons, which is a Poisson statistics of a coherent light beam. So again, because if you can trace this, the origin of the particle term here, the Poisson statistics, the shot noise, if you like, to the non-commutivity of the A's and A daggers. But it's marvelous how Einstein inferred that without having to do any commutators or anything like that. Okay. I'll just show quickly something. I think it was Maxwell who first pointed out that there might be something wrong with classical physics. In 1850s, not 1959, 1859. Time flies, but not that fast. Okay, in 1859, he first suggested that classical physics might be wrong because it failed to account for how specific heats depend on temperature. You know, the freezing out of degrees of freedom, quantum mechanically thinking, as T goes to 0. There were some experiments by Eucken on the contribution of the rotational degrees of freedom of molecular hydrogen. And this is Eukken's data. This is what you get with the standard sort of theory at the time. It's horrible agreement with experiment, right? What Einstein and Stern did was assume that rotational motion, like harmonic oscillator motion, also has a zero-point energy. And by doing so, and with one adjustable parameter involving the moment of inertia of a molecule, and the number they had to use to get this marvelous agreement was in fact very close to, if you just take a diatomic molecule and the average separation, mr squared, you get essentially very close to what they had to assume for this adjustable parameter. So it was a remarkable agreement which Einstein said was splendid. So that was the second reason why Einstein felt that zero-point energy was real. But being such a remarkable genius, he later discovered or decided in a letter to Ehrenfest that the idea of zero-point energy is dead as a doornail. I have a feeling why he felt that way, but it would be too much of a digression at this point. I think this is wrong. I think we now have lots of experimental, conceptual evidence, if you like, that zero-point energy is alive and doing quite well. In fact, Mulliken in 1923, again before commutation relations and any of that stuff, he found evidence for zero-point energy in the vibrational spectra of diatomic molecules. What he did is he looked at two isotopes of oxygen in the molecule boron oxide. He looked at the vibrational spectrum. And if you assume that there's an energy, a zero-point energy, 1/2 h bar omega, and the omegas depend upon the mass of the oscillators, this gets a little technical, but in the 0 to 0 vibrational bands, he found that you needed the assumption of zero-point energy to give you the correct difference in the 0 vibrational bands of those two isotopic molecules. So that was, I think, pretty strong evidence for zero-point energy, which isn't often mentioned. We have other examples, of course. You know, the idea that liquid helium stays liquid at low temperatures is because helium-4 is bosonic and it has zero-point energy. So, and it's light, you know, so the zero-point energy is pretty large. X-ray diffraction, if you go to zero temperature, there's still not perfect coherent X-ray diffraction, and that's associated with a zero temperature Waller factor, that sort of thing. So we have lots of evidence for zero-point energy. I mentioned earlier in the late 40s that there was the extremely important work on the lamp shift and so forth, that zero-point energy ideas were invoked. I won't go through this in any detail because it's simple but straightforward. The argument is, Feynman expressed it in terms of a forward scattering amplitude, and Power, I think, deserves most of the credit because he expressed things in terms of a refractive index, which of course is related to the forward scattering amplitude. The basic idea is as follows. The basic idea is due to Feynman, though. Consider a dilute gas of n atoms per unit volume in a big box, okay? Look at the change in the zero-point energy in that volume in that box due to the mere presence of the gas, all right? So with the gas present, the zero-point energy is 1/2 h bar omega times h bar omega divided by n, right? Because your wavelengths are, your allowed wavelengths are fixed, you know, an integral number of half wavelengths, all that stuff. So you change the frequencies by dividing by n. For an infinite box, or for no molecules present, no gas present, it's of course this. The idea is that the change in the zero-point energy due to the presence of the gas is just this difference. For n approximately 1, it's approximately this. Okay? Now we know what n is from the Kramers-Heisenberg dispersion formula. We can write it down in terms of the transition frequencies in the matrix element, so there should be an m sub mn here, transition dipole matrix element. And if you write that out in terms of not 1/2 h bar omega, but in terms of the expectation value of the electric field squared, you can write it like this. So this is nothing but a quadratic Stark shift that comes from the idea that you look at the change in the zero-point energy due to the presence of the gas. Now you go to the limit of one atom by taking n sub v going to 1. So here. You have to do so. What you get by plugging into that formula, of course, is an infinite quantity. But now you argue that, well, to obtain an observable shift, I also have to subtract the energy of the free electrons, because I'm interested in the energy of the bound electrons compared to when they're free. So I subtract out the energy of a free electron given by taking the limit is that goes to 0. Right? The omega sub n's go to 0 because you have now a continuum of energies. So I just get a quadratically divergent term by throwing that away. Subtract that from here, you get that. And now you follow Hans Bethe and you say that I still have an infinity, this time a logarithmic infinity, but I assume that the lamp shift is basically a non-relativistic effect, so that only frequencies up to mc squared over h bar contribute. So I cut the integral off, and I get that. You plug in all the numbers for hydrogen, the matrix elements, and the energy eigenvalues, and so forth. Take the limit as nv goes to 1 for case of one atom, and this gives the famous beta logarithm term contribution to the lamp shift, which gave something like 1,040 megacycles compared with the experimental 1,057 or so. And Feynman called this the most important development in the history of QED. And you can see how closely it's related to zero-point energy. And that is the lamp shift. The Dirac theory without coupling to the zero-point radiation field would say that all states with the same n and j would have the same energy. They would be degenerate. The lamp shift is the experimental observation that that is not so. And it's because, according to that simple calculation, it's because of the coupling of the atom to the zero-point fluctuating electromagnetic field. I gave this talk a couple of months ago at Rochester, and I wanted to point out my first advisor at Rochester was Bruce French, and he was a longtime professor at Rochester. Turns out he was also Canadian. He served in the Royal Canadian Navy before going to graduate school in the after the war at MIT, and he worked with Weizkopf. And the interesting thing here is that French and Weizkopf actually computed the Lamb shift and got results that were different from Feynman and Schwinger with their newer techniques. They had to evaluate like 75 integrals or something, really, really complicated old-fashioned perturbation theory. It turned out they were right and that Feynman and Schwinger were wrong. And in one of Feynman's papers in the late 40s, he says in footnote number 13, unlucky number, that the result given in B in equation 19 was an error, was repeatedly pointed out to the author in private communications by Weizkopf and French. Feynman, it turns out, was the referee of their paper and repeatedly said, I guess, that he didn't think it should be published because it was wrong. Blah, blah, blah. So the author feels unhappily responsible for the very considerable delay in the publication of French's result occasioned by this error. This footnote is appropriately numbered. Well, what's funny about this is that if you look at the paper, there are footnotes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11A, 12, 13. So he obviously, I think, fudged it so that this would come out to be footnote 13. Okay. Now finally back to Casimir. I could tell an interesting anecdote relating to this if anybody's interested, but maybe it'll have to wait. Okay, so with such a simple derivation of the Lamb shift, a lot of just fudging around with algebra, but it's really simple, right? So let me now try to give an equally simple derivation, maybe even simpler, of Casimir's famous formula. So we go back to two parallel, perfectly conducting plates. We know about this stuff, right? You have to have wavelengths small enough to fit inside the box, otherwise modes with larger wavelengths are not allowed. If you take a cavity and you put an excited atom inside the cavity, and the emission wavelength is large compared with the size of the box, the atom doesn't radiate, it stays there forever. There have been experiments on this sort of thing. So we know that to be true. So you have to have frequencies larger than this number in order to have allowed modes. So let's go back to the idea of zero-point energy. Remember I said we had a spectral energy density, in the interval omega to omega plus d omega per unit volume was given by h bar omega cubed over 2 pi squared c cubed. So the total zero-point energy should be what? That's per unit volume, so I multiply by an area, some area, distance between the plates, that gives me a volume. But when I do the integral, I cut it off. I cut the lower limit off at something on the order of that. Well, this is for one dimension. We want to talk about 3 dimensions, so it would be reasonable to assume that this coefficient beta here multiplying that should be on the order of 1/3. Okay, that should be the physically meaningful zero-point energy of this box. So I call upon my knowledge of integral calculus. I can rewrite the integral, right? So I have this integral from that to infinity, so I rewrite it from 0 to infinity minus this. Well, that guy, that's like a bulk volume contribution. As I double the size of the box, I double the energy. It's what Schwinger called a volume energy, because we want to get rid of it. So let's ignore that term. What we're left with is that, which we'll say is the physically meaningful part. Maybe not with such impunity as before. But anyway, so we do this integral. You can see that because of the omega cubed, I get an omega to the 4th, so I get a 1 over d to the 4th. I get the right distance dependence for the interaction. Now, I said beta should be on the order of 1/3. I can fudge around with that a little bit. Let me take it to be 0.325. That's close to 1/3. And you'll all remember that that's equal to 1 over 90 to the power 1/4. Okay, joke. Okay, I don't want you to feel inadequate. Okay, so I use that number here and I get exactly Casimir's result. Okay, this is the result that Schwinger said was non-intuitive and Bryce DeWitt was shocked to hear about and has now been measured. Here's a maybe even simpler derivation going back to a fairly old paper. This was based on the calculation of the stress tensor for the vacuum field. But the basic idea is simple. You just assume that you have virtual photons flying around, each one with a momentum 1/2 h bar omega. Okay? So what's going on? You have these virtual photons at 0 temperature bouncing off the plate. They tend to push the plates together. Right? Photon bounces off, the plate has to recoil, likewise here. On the other hand, photons inside, they tend to push the plates apart. Right? Bounce off here. You have more modes. You have an infinite continuum of modes out here, and only a discrete number of modes here. A denumerably infinite number, but nevertheless. Right? So there's more pushing together than pushing apart. And in fact, if you go through the algebra with the stress tensor, you find exactly Casimir's result. So that's a very intuitive derivation, a little superficial because I'm dealing with two infinities again, but nevertheless, I do this subtraction. Physically, I can conceptualize that there should be an attraction, and it works out that you get exactly the right answer when you go through the algebra. Okay, now, the origin of the Casimir effect was in these van der Waals interactions, right? I think one should emphasize that the Casimir effect is really, in a sense, nothing but the macroscopic manifestation of van der Waals interactions. So to justify that assumption, let me go back to the force between two molecules. Remember we had this 23 skidoo? Anybody who's heard that expression? So if I consider an atom near a wall. Atoms here, one atom here. I just add up all the van der Waals interaction. It's one of these integrals that we used to do as freshmen. Maybe now you do it on Mathematica. But you get this. Just adding up the pairwise 1 over out of the 7th van der Waals interaction. Now remember Clausius-Mazzati says that epsilon minus 1 over epsilon plus 2 is n, number of molecules per unit volume, times the polarizability divided by 3 times 4 pi, something like that. So I replace the polarizability squared, replace one of the polarizabilities by Clausius-Mazzati. I keep the other. And now I say, well, let me go to the limit of a conductor now. The limit of a conductor is epsilon, the permittivity going to infinity, right? So I replace this quantity by 1. I'm left with just this, which is that. The exact answer is that, but you can see that this is pretty close. If I multiply the 8 pi by 20, I get 160. If I multiply by 3 by 20, I get 60. Well, I have a 69 here by this simple argument. This is within 15% of the exact answer. So you get almost the exact Casimir-Poulter result. Yeah.
What does it mean to be approximately the right thing? It seems to me that...
I'll come back to that. The key is that I've added up pairwise interactions. This atom with that atom, that atom with that atom, and so on. Okay? Good point. Very astute observation. Let's do the same thing for the Casimir case now, the two plates. Let me start out with two dielectric plates. Add up the pairwise van der Waals interaction. So I take this guy, add up all the van der Waals interactions with all these molecules here. Then I do the same with that guy and add everything together. You get, now I replace the polarizability squared by Clausius-Mazzati squared. I again say I'll go to the limit of a perfect conductor, replace this by 1. You get this compared with the exact answer. That's within about 20% of the exact answer. So it at least justifies the idea that what the van der Waals, what the Casimir interaction really is ultimately is just the interaction between molecules. And in this case, I've gone to the perfectly conducting limit. But there should be nothing mysterious about it. In particular, I haven't even invoked zero-point energy here, right? So, to come to Professor Laflamme's point, why didn't we get exactly the right answer when we add up these two-body van der Waals interactions? It's because van der Waals interactions are not pairwise additive. In electrostatics and Newtonian gravity, you can add up pairwise interactions and you get the right interaction, total interaction. Van der Waals doesn't work that way. I'll try to motivate that a little bit in the next few minutes. So how could we do a more rigorous type calculation? Well, this will be a sort of poor man's many-body theory. You can do it more rigorously or fancy or whatever, but I'll just try to give an intuitive, simplified argument. So how to calculate van der Waals interactions between macroscopic bodies like these two plates, given that we cannot just add up the two-body van der Waals interactions, because if we do, we get the wrong answer. Close, but not close enough. Let's first recall that in the Lamb shift calculation, we use the formula for the Stark shift. So let me argue that for an atom at some position R, this is the change in its interaction energy in its energy level, even I could say, compared with when the atom's in an area where I can ignore that term in infinity or something. And remember the relation between this and the zero-point energy. This is the vacuum field. expectation value of the electric field in vacuum is not 0 because you have to have 1/2 h bar omega per mode of energy. So E squared plus H squared expectation value has to give you that 1/2 h bar omega. So let me just start out with that simple formula. And I mean, this is in Jackson. I induce a dipole moment P equals alpha times E, but the dipole moment is induced, and so to induce it, I have to change the electric field, from 0 to E, or you get 1/2. You get 1/2 alpha E squared. So the 1/2, this is the dipole energy minus P dot E, but I need the 1/2 because the dipoles are induced by the vacuum field. Okay? So let's see what we get. So consider an atom at some position r sub I. It's surrounded by all these other atoms, which may make up a wall or half space, or maybe just one other atom, whatever. The field at that point is the vacuum field in the absence of any sources, field with corresponding to an energy 1/2 h bar omega per mode. But now I also have the dipole fields from all these other atoms acting on, from the superposition principle contributing to the field at r sub I. And you can write that in a fancy way. This is nothing but the 1 over r plus 1 over r squared plus 1 over r cubed, but I write it as a curl, okay, to simplify notation. And the electric field here at Rj is the exact electric field. Right? So this is if I replace this by an integral, I just have an integral differential equation for the electric field. But let's just stick with the discrete summation. So what we do now is just iterate. Right? First approximation, just ignore that term. This guy's just sitting in vacuum. Next approximation, replace the E here at Rj by the vacuum field at R sub j. Right? And then keep going. Just keep iterating. So the first trivial iteration gives you, I just wrote the formula here again. The first approximation here gives you just the Lamb shift that I showed earlier. It leads exactly to Beta's famous expression. The next approximation, where I replace this E here by E0, and now I have to square to get the Stark shift, if you like. So I get a cross term, an E0 at Rj and an E sub 0 at Ri. That gives me exactly the sum of the pairwise van der Waals interaction. So what this says is that the van der Waals interaction actually does involve 0-point energy. Why do two molecules interact? They're just sitting in vacuum at 0 temperature. It's because I have this 0-point fluctuating field inducing dipoles in these two atoms. And because the electric field at R sub I and R sub j is not 0, the product of the field expectation value is not 0, it falls off rapidly with distance. But at small separations, it's not 0. The vacuum fluctuations are correlated. It's because of that correlation that these dipoles that are induced by the vacuum field dance in phase and attract each other. Okay? Now, what's the next order? That's just what I've just said. What's the next iteration? It's complicated, but what you find as it goes, of course, is alpha cubed. But now it goes as the interaction between among three molecules, R sub I at R sub j at R sub k, goes as 1 over the cubes of their various separations. And in fact, the numerical coefficient that you get by this simple approach is exactly what Axelrod and Teller derived. This is Edward Teller in 1943. Another interesting thing about this formula is it not only indicates this non-pairwise contribution to the van der Waals interaction, but it also shows that if you arrange the molecules appropriately enough, that you can get a repulsion as well as an attraction. So they looked at various examples where you put the molecules on a line or on a triangle, that sort of thing, and you can get attraction or repulsion. So from this point of view, van der Waals interactions are non-pairwise additive because of multiple scattering, right? So coming back to my simple picture here, if I want to know how this atom interacts with that one, it's not just the field from this guy coming back here, but it's a field from this atom which can scatter off that one and come back to here. So you see the field acting on this atom, and it's all very simple, but it's multiple scattering, right? This guy can, if you think about it in terms of source fields, this can radiate a field which scatters off here and scatters off there and so on. And I add up all these multiple scatterings. And you can do this diagrammatically, and you get, in fact, what I just showed. So, but can we do this? Can we do this more simply? Can we, instead of having to resort to these multiple scatterings and iterations, can we get is there any simplification possible? The answer, of course, is yes. I can replace the summation by an integral. All right. And the nice thing about that integral is that its solution is known. It's known on the basis of the so-called Ewald-Assien extinction theorem that you can read about around page 100 of Born and Wolf, for example. What the theorem says is that the solution of this integral differential equation has two pieces. One piece that comes from the integral here exactly cancels the incident field. So I've got this medium. Light comes in propagating at the velocity c in vacuum. What propagates in the medium, though, goes at c over n. How can that happen? Because of the superposition principle. You add up all the fields. Well, what happens is, in fact, that the part that goes to c is exactly canceled. What's left is second part of the theorem is just, what's left is just the part that goes to c over n. So the Ewald extinction theorem says, therefore, in effect, that instead of solving this multiple scattering problem, you can just write down Maxwell's equations. Okay? Because this gives you the same, it's just the integral form of the differential Maxwell equations. So having done that, the simplest approach, now I go back to the idea of zero-point energy, right? So the theorem, based on multiple scattering and going to the continuum limit, says that I just solved Maxwell's equations. I found out what the allowed frequencies are. I get some transcendental equation, f of omega equals 0, and I want the sum of the zeros of this function because I want the sum of the 1/2 h bar omegas. There's a theorem called the argument theorem, which says that in which I can relate the integral, contour integral of f prime of z divided by f of z, integrated over some closed contour. That integral is equal to the sum of the zeros, which I want, minus the sum of the poles. It turns out that the poles don't depend upon the distance between the plates, between the objects, so I can ignore them. And so once I solve Maxwell's equations, get that equation, I can now determine what the sum of the 1/2 h bar omega is. And this is not the way people are solving Casimir forces for arbitrary geometries. The approach is based on the Green function, dyadic Green function, but the underlying basis for that, based on the extinction theorem and the Maxwell equations, is from the microscopic intermolecular business, is the same. You get complicated things. This is in the field, it's a famous formula due to Lifshitz. And these guys obtained it, in fact, from many-body quantum field theory. But you can get it much more simply, as is done in this book, by what I just showed. So, okay. Now, I should, in the last minute and a half, I should point out that there are other ways to understand vacuum effects, the Casimir effects. Schwinger did not believe at all in vacuum fluctuations. For him, the vacuum was just a trivial zero state, no physical properties of any interest at all. So it was a challenge to his source theory to be able to derive Casimir effects from the point of view of source fields rather than vacuum fields with zero-point energy. And he was able to do it. Very few people can understand, as usual, what Schwinger actually did, because he starts out with an action principle, which doesn't come from a Hamiltonian or a Lagrangian that anybody. Anyway, but you can reproduce Schwinger's results in a conventional version of his theory, in which you normally order various operators. Normal order, as many of you probably know, you can eliminate zero-point contributions. It's an annihilation operator acting on a vacuum state gives 0. So if you normally order, you can derive Casimir's results. If you use a symmetrical ordering or an anti-normal ordering where a dagger acting on the vacuum gives non-zero, then you're back to the Casimir picture of zero-point energy. And I've already mentioned the radiation pressure approach. We've also discussed an image method, which, for the Casimir polar case. Jaffe at MIT recently has sort of rediscovered what I was saying earlier. Just quickly in one more minute, just to give you some idea of why is there this close connection between the source field approach of Schwinger or conventional QED with normal ordering and the vacuum field approach. Let me write down the equation of motion, Heisenberg equation of motion. These are operators for a free electron interacting only with itself. Right? This is the radiative reaction part. The stuff in Jackson, X triple dot. And it's also seen, of course, the 0 point field. So just an electron in vacuum, nothing else in the universe, what does it see? It sees two fields. One is the field acting back on itself. That's that term. The other is this 0 point vacuum field. Why are these two so closely related? Well, if I solve this formally by expanding this in a Fourier series and then calculate the commutator, you get this. Now remember, and the omega cubed here comes from the fact that this is a third derivative. Now remember I said that this spectrum of 0 point radiation was very special, this thing that went as h bar omega cubed over 2 pi squared c cubed. The omega cubed here that comes from this cancels that guy. I get an integral, which I can do, 1 over that is equal to, all that stuff is equal to just IH bar. So this is an example of the fluctuation-dissipation relation, only in this case applied to the 0 point vacuum electromagnetic field. It says that the dissipation, which goes as x triple dot, is related uniquely to the spectrum of the fluctuations, which goes as omega cubed. So if I had just an ordinary frictional damping that went as x dot, I would have to have a 0 point spectrum that went as omega, right? First power of omega, first derivative with respect to x, and so on. Whatever complicated form you assume for the dissipation, it has to be reflected by a fluctuation, simply to preserve commutation relations. You cannot have dissipation without fluctuations. Vice versa, you can't have fluctuations without dissipation. This is the upshot of the famous Callan-Welton paper in 1954 or something on the fluctuation-dissipation relation. But in this context, it sort of helps us understand better why we can obtain Casimir effects not only via the vacuum field with this omega cubed spectrum, but also via source fields a la Schwinger. Okay, and now I probably should not. I'll talk about Casimir's. All right, and I'll try to do it in 20 seconds. Casimir said, let's suppose that the electron is really just a perfectly conducting sphere with some charge E. The Coulomb interaction is that, so that causes the electron to explode, right? But he said, suppose I've got this Casimir attraction. From dimensional grounds, it has to have this form. It has to go as h bar, it has to go as 1 over the radius, right? This is the force per unit area. Some constant c here. If these two are to balance, the electrostatic repulsion is going to be balanced by the Casimir attraction. C has to be equal to what? Turns out, if you go through that little algebra, it has to be exactly the fine structure constant. So therefore, by measuring or calculating the Casimir force on a sphere, you can get the fine structure constant. Right? Wouldn't that be amazing? Unfortunately, this problem was posed to Timothy Boyer for his PhD thesis at Harvard years ago by his thesis advisor, Sheldon Glashow. What Boyer found, what he called a long nightmare in classical special function theory, and at least 3 other groups have confirmed his result since then with perhaps different coefficients out here. But what he found was that the force was in fact repulsive. So even Casimir, with his vaunted physical intuition, didn't get that right. He thought a sphere there should be an attractive Casimir force. Turns out to be repulsive. There are other examples. You can take cylinders, and depending upon the aspect ratio, you get an attraction or repulsion, whatever. So the forces, the sign is wrong. You don't get. So that's what he said. It did in that letter. It did not lead to the fine structure constant. So, thanks for your attention.